So I'd like to introduce Dr. Danny Kent, and Danny is a doctor of robotics, and he's working with Orion, and they have a great demo over there. If you walked into the area over there, you walked right through their demo, and I found a lot of value in that, and I'm sure he's going to elaborate on that and a lot of other things today. But we had a conversation earlier, and I was just really impressed with the amount of things that he's looking at, issues and problems out there that you can solve through, again, if you know me, then AI is something that I'm really excited about, and virtually solving problems through robotics and AI. So without further ado.
Thank you. Good afternoon. So I'm going to be doing a bit of a presentation talking about LiDAR. Chris did a pretty good introduction, but just a quick induction who I am. So I have been working in mobile robotics since the year 2000. And over the course of my career, I've had an opportunity to do a lot of really cool things. One of them being this event called the DARPA Grand Challenge. So this was in the mid-2000s. DARPA put out a challenge in defense advanced research projects. They would give $1 million to a team that could build a robot that could drive 140 miles across the Mojave Desert, completely autonomous, and average 15 miles an hour. So the first year is 2004, abject failure. Best robot went 7 miles. But to their point, to being able to push the technology forward, in 2005, 10 teams completed the course. So that's kind of foundational for me. My background during DARPA Grand Challenge was geospatial information and tracking objects relative to the vehicle and understanding where those objects are and where they're going. So here today, I'm here to talk about a technology called LiDAR. Who knows, understands, thinks they know about LiDAR? Just raise your hand. All right. So that's why there's some introductory material. So LiDAR is a hodgepodge of the word radar, right? Essentially, somebody wanted to figure out how to educate people about laser range finding, and you have radar finding, so we're just going to mash the L in the front of the word radar, and we come up with LiDAR. It doesn't actually mean anything. But what it does is it uses lasers, typically in the near-infrared range, to shoot a beam, count how long it takes for that beam to come back, and essentially you're doing a time-of-flight ranging, right? The output of the sensor is what we call a point cloud. So a point cloud is essentially just a very large collection of discrete points in space that the laser knows are a solid object. One of the features about LiDAR that I don't think people appreciate fully is that LiDAR is what we call self-illuminating. And why is that important? It's important because, unlike cameras, we don't need light to see the world. The LiDAR itself is illuminating its target with its laser beam, so we get exactly the same performance in day, night, and all kinds of weather. So the question here before us today is, what do we do with LiDAR for spatial detection, person detection, things like that? Why do we use LiDAR? Well, first, I consider the information to be very rich. So back in 2000, LiDAR, I paid about $9,000 for about 80,000 points per second, or per minute. Nowadays, I get upwards of 5.2 million points per second for about 4K. So the information is very, very rich, a whole lot of information, very dense, high resolution, and it's also very fast. So we get this data at 20 hertz, which is close to real time. Don't get me in my discussion about what the definition of real time is. The other thing that's really nice, and particularly for this audience, is that because we're talking about geometry, there's no identifiable information. We don't know color of skin, we don't know color of clothing, we don't know facial features. All we know is the basic geometry of the object of interest, right? So the geometry of a person is pretty much consistent, right? What's also nice about using geometry is it scales, right? It's essentially it scales up and down, and the overall geometry of a child and the overall geometry of an adult are the same. They're just a scalar. So what this now allows us to do is a couple things. It allows us to build a system that's capable of identifying, tracking, and classifying objects in real time with no personally identifiable information. So in comparison to LiDAR, radar, cameras, this is a little plot chart that somebody else made up. I blatantly stole it, but it kind of gives you these 6 or 7 key attributes that these sensors all share and kind of points out the strengths and weaknesses. So one of the important things, which of these buttons does, there it is notice color information. Cameras, very high amount of color information, right? Very high resolution. LiDAR and radar, 0 color information, right? We don't understand anything that's unique about a person's color. Lighting conditions, very, very good in comparison to your cameras. And resolution is pretty much equivalent to cameras nowadays. I can get imagers that are 320 by 240 or 640 by 480. So essentially low-end cameras, right? The other interesting thing, and the reason that I personally got into this space, is that LiDAR was traditionally, as the example I gave, kind of costly, expensive, right? You have these on every one of the Google self-driving cars, the Waymo cars, the Cruise cars, and the ones they strap on there are $10,000, $20,000, $60,000 sensors. But because one of the main drivers of the industry is the autonomous car market, you can see that this is just one metric I chose, but it's kind of nice because it scales across different makes, manufacturers, resolutions, is how much am I paying per point, per second? And you can just see the exponential curve. So this is 2D sensors. This is 3D sensors. This is approximately where we are now. This is a collection of about 6 different manufacturers and the different LiDAR sensors. So now I want to talk about traditional applications. So where is LiDAR used today? Does anybody use it? And so traditional applications, as we already mentioned, the big elephant in the room is self-driving cars, right? Unless you're Tesla, and Elon Musk is wrong, everybody else uses LiDAR. Mobile robots, that's kind of my background. That's where I came from. A lot of warehouse robots, things you guys might be familiar with like Nightscope, they all have LiDARs on them. Aerial surveying, if you're not familiar with this one, it's really, really cool. Go home and Google it. Search for something about Mayan ruins found in Colombian rainforest or something of that nature. The way they're finding this is by flying LiDAR on drones. LiDAR has a unique ability to kind of see through the canopy and actually give you information about what's on the ground. And they're making lots and lots of discoveries of lost cities. Another important, and this one's growing rapidly, is what we call intelligent transportation systems. So these are systems that allow you to monitor the traffic in your city, make decisions about lights, opening up alternative lanes, tracking people, watching for accidents, things like that. Essentially make your city what people call smart city. But the applications I want to focus on today I think are more interesting to you guys. And that is applications in which the important information, the information we're interested in and the information we're making actionable choices about are related to people, their position, their orientation, where they are relative to something else. Whether it's an automated machine, whether it's a static sensor, how do we build applications with LiDAR that interact with people? So first I want to take a step back, talk a little bit about my company. Name of my company is Mechaspin, and we have a proprietary custom product that we call our MSX processing engine. What it essentially is a collection of software that we've written that optimizes the processing of this very, very large, high-density set of data. One of the key features that we developed is something we call sensor agnostic. So every manufacturer's sensor, every make and model of their sensor, we pull that information into a common data format, which allows us to apply any of our algorithms on one common data format. So we're not reinventing the wheel every time we add a new sensor. The other thing that inherently is nice about this is that we can fuse multiple sensors together. So on self-driving cars, in the last 5 years or so, you've gotten to a situation where there's more than one LiDAR sensor on them. But in general, a lot of the solutions that are out in the field are one sensor, one compute module. That's the view of the world. We're interested in how do you bring 4 or 5 sensors in different locations, fuse them into one picture of the world, and make decisions about the world based on much larger sets of data. We have a unique implementation of something that's called multi-object tracking. This is essentially how we track in our LiDAR data where something is, where it's been, where it's going. And that uses something called multi-hypothesis tracker. And then what we have is something we call the neural processing unit. And the neural processing unit is focused on these 3 things, which is matching features. So if you want to find where a basketball is in your scene, if we have a pattern of what a basketball looks like in LiDAR data, we can find it in your scene. If you want to find out where pretty much any object is, right? Bin picking, things like that. Anomaly detection, so we can look online at the data and say, something's not following some nominal path of data flow. Something is awry. And the last one, the one I'll talk to the most today, I'll put these in reverse order, is object classification. So this is, I believe, very unique. I think that we are among the only people that's using AI and machine learning on point cloud data. And what that means is you're probably very familiar with using machine learning and AI techniques on camera data. Camera data is inherently 2-dimensional. LiDAR data is inherently 3-dimensional. So we believe we're the only ones that are taking fundamental 3-dimensional information and putting it through a neural network and getting actionable information out of it. At least commercially. Obviously, it's done in academia a lot. So I have some use cases I'm going to walk through now. That's all the background material. The boring stuff's out of the way. So hopefully this is more exciting. So the first example I'm going to talk about is this autonomous strawberry picker. So this is a customer of ours. They're down in Plant City, Florida. It's about 2 hours from where I live. And they built this massive machine. They call it the harvester, or B4. And underneath this machine, where you can't see, right in here, is 12 robotic arms. Those robotic arms pick strawberries off the plant at the rate of like 2 per second per arm. But what we worked on, we had nothing to do with the arm. But what we worked on is the harvester. And in particular, what we were interested in is building a collision avoidance system, right? So this particular customer had a really interesting, unique need. They couldn't get insurance on their vehicle unless they had a collision avoidance system, and they didn't have a collision avoidance system, and they had to get insurance on their vehicle. So they had a chicken and egg problem. So we kind of quickly spun up this collision avoidance system for them. So what we see here is the red dots are the strawberry fields, the furrows and the plants. The yellow dots are people or things that are not part of the crop. And then we're tracking them, clustering them. So this is probably pretty familiar. You got a bounding box around the object. And we're telling the control system for the robot, hey, I think there's an object here. Here's how far away it is. And they make a decision. Do I want to slow down? Do I want to stop? So on and so forth. There's another bit of this. It's interesting. We also built for them, using the same set of data, a row alignment system. And what that does is it detects the edges of the rows, and it ensures that their vehicle is driving down the middle. They have an 8-inch wide tire and a 12-inch wide gap between crop. And they have an RTK GPS with a 4-centimeter error. That means they're right on the edge of driving over the crop. So this data is now being used for 2 different applications on the same vehicle at the same time without investing in more infrastructure. So the second example I want to show is something that we call internally fork alert. It's a fork truck safety system. It's an advanced driver awareness system for fork trucks, right? In 2019, we built this prototype, and essentially you have one LiDAR sensor mounted on the back of the vehicle, and you have this analog output that tells the driver how close to an object they are. Now, next month, we're deploying this system. This system is for a much bigger truck, and this customer has a very large truck, and they have these A-frames full of glass. This is specially coated glass. It's very, very expensive. When they have an accident, because it's glass, it tends to all break, unfortunately. So it's kind of like a bad situation. So get to another. This is the vehicle. You can see here, it's quite a large fork truck. What we've added, and what makes this a little bit more interesting for customers, is we've now added the ability, instead of just finding something and figuring out how far away from the sensor it is, we now have zones of interest. So now in this vehicle, we have these 3 zones that you can kind of see in here. And now what we do is we take the vehicle kinematics into account. So instead of just saying, oh, this object is X amount of close, you might hit it, we're now taking the kinematics. For those that aren't familiar, kinematics is essentially the geometry of the vehicle, the geometry of the drivetrain, the geometry of where the steering wheel can go, left to right. Ackerman steered vehicle, this is the profile it would drive if you turn the wheel all the way one direction, this is the profile it would drive if you turn the wheel the other direction. It's just the physics of the system. And so what we do is we take these 3 zones, and we're actually calculating now how close an object is to hitting the vehicle, instead of how close an object is. And so these operators, this is actually an operation like we just saw. So if you watch this, this is a 3-dimensional view. This is a top-down view. That's the platform it's going into this A-frame. And then these are objects off to the side. And we have an analog LED light output. It's now segmented into 3 sections. The old one was just one big section. You probably saw it getting smaller and bigger. We've now segmented in 3 sections for the 3 zones. Another kind of pivoting here, those are applications on moving vehicles, right? Sensor is moving relative to the environment. Things in the environment are moving relative to the sensor. These are a little bit more static applications. So what we call this is our MSX tracking engine. What the tracking engine does is it uses LiDAR data to filter out the background and only look at interesting points that were not there before. And then cluster those points. Clustering is a technique in which you look for a big, large chunk of data that's all together in the same space, and then tracking them from frame to frame. So first thing to note is this camera is not part of the system. That's just a GoPro I plugged in, synced the video. But it's hard, unless you have worked with LiDAR data for 20 years, it's kind of hard to look at LiDAR data and know what's going on. So this gives some contextual awareness. So these are the people walking around, and you can see them being tracked. Our tracking system is identifying that as a unique object and associating the same ID to the object from frame to frame. That's important. Once I know something is an object, once I know where it is, and once I know where it's been, I now have really rich data about that. I know where something came from, and therefore it means I also know where something is going. I know the intent of an individual as they're walking around. This system also supports classification. So we'll get into classification a little bit later, but essentially any object you see, using AI, we can train the system to understand that object's class. So if we wanted to train it for vehicle versus motorcycle versus pedestrian, that's all, doable in 3-dimensional space. So now we'll get into a couple products that we built in conjunction with Orion. So we've been working with Orion for about 3 years. We've built several products, but these are 2 highlights. The first one is called SmartGate, and I can't remember what Mike Johnson told me to call it, but it's some intelligent person entrance thing. I don't know. So this is a really good overview of how we typically work. Let me go back. So first we start in simulation. So this is a simulation environment that we have built. It's custom, it's ours. And it simulates LiDAR data in a nominal form. So it's like perfect data, right? And anybody that works in sensors knows there's no such thing as perfect data. But it gets you started. And then we go into real-world testing, which is the second section of this, and it kind of shows you from the top down what the data looks like, right? So here we go. This is our zones. This is our people walking through the zone. And you can see our tracking system, so it's identifying unique IDs. One thing that's really cool about this setup is that we were able to identify the intent of a person. So if I walk parallel to this gate, it doesn't open, right? If I walk towards the gate, it opens. And that's all because we can predict the velocity of the object that we're tracking based on where we know it was and where we think it's going. And so we know the direction of travel, and then we can infer where we think that person is going. And then the big one. I saved the best for last. This is what they were talking about. Is over there. You can go look at it. It's hanging up over the main entrance, and it's a product called DoorGuard. DoorGuard is an anti-tailgating solution, or at least it started that way. And by the time we got to where we are today by solving the anti-tailgating solution, we also figured out that this is a very accurate and very powerful person tracking and person counting system, kind of byproducts of what we had to do to solve the other problem. So I'm going to show you some examples. I consider these the most complex examples. So there's no simple example in here. The first one is two people walking together holding hands. And what you can see is this is what's called a range image. This is your top-down projection. But those people are so close together that the system would typically consider it to be one person. What we've done is, and I have a slide on this next, is we have trained our neural processor to understand the difference between what one person looks like and two people look like. This is one person hanging out by the door while other people enter and exit. Very tricky, right? That person is standing there as people come through. Are they a new person? Are they part of that old person? Is that a person that moved in front of the door from last frame? These are all kind of tricky scenarios, but our tracking system is accurate enough that it handles that because it's built on what's called a multi-hypothesis. It uses a common filter. Is this the end of the video? I think it is. Oh, an important note. This is a representation of the data. This is not data that comes out of the sensor, right? So we don't get color or video or anything like that. This is a way of projecting this three-dimensional data into 2D space using the camera's orientation. It's what's called a range image. The colors correspond to how far away from the sensor that particular point is. So you can see here two people walking shoulder to shoulder, and we track them as two separate objects. And if we had what we call counts in here, you'd see 2 exits, 2 enters, things like that. So the last thing I want to talk about is our neural processor and how this works. So Chris was talking earlier. He's really into AI. AI is a funny word. I don't like it. But AI, neural network, machine learning, whatever you want to call it. So how is this done? So we have our own custom neural network that we've optimized for point cloud data, for 3D data. And we start with telling it, this is what a point cloud of one person looks like. And then we tell it, this is what a point cloud of 2 people look like. And then you throw some more data at it. And then you throw some more data at it. And then you throw a lot of data at it. A lot. So we're on the order of magnitude of 100,000 frames in our training set right now. But the goal is, by the time you do all this, what you can do is ask the network whether that object are one person or 2 person. To date, we have about a 99.6% accuracy with this, and it runs in what is essentially real-time 11 milliseconds, so 100 hertz. The sensor is only running at 20 hertz or 17 hertz or 10 hertz, depends on the configuration. So we keep up at frame rate of our sensor. Okay, so hopefully there's a few things I want you to take away from this talk because it's a very technical talk and I understand if you've been bored. The first takeaway is that a little bit about what LiDAR is, right? So key features of LiDAR, self-illuminating, very accurate, completely anonymous, and cost is falling, which is important. we didn't cover this too much, but just know the fact that more and more powerful compute capability is being packaged in smaller and smaller and cheaper pieces of hardware, which allows us to take the type of data that I used to use when I was, the mid-2000s, and we had a server rack per student, per project, an entire one-use server. And we can do that on a processor that big now. Matter of fact, we can do it better on the processor that big than we could do on a one-use server in 2005. And I think these are important, and this is my statement, others can disagree, but detecting, tracking, and classifying are not research projects. They are solved. This is not research. This is turn the crank, deploy engineering and good know-how to a problem with a well-defined structure. And the last thing I want you to take away from today is not an understanding of what LiDAR is, not an understanding of the use cases we've looked at. What I want you to take away is one question to ponder. And that question is, what technology gaps are you familiar with that you think LiDAR and the type of technology and use of LiDAR that I've shown today could address you and your customers' needs, right? This is not me trying to convince you to buy any of the things we've already done. What I want you to do is be able to think about LiDAR and these types of problems in a new light. So now, I'm hopeful you guys are going to have some questions.
Earlier you were saying that the LiDAR, as something comes into its entrance, it not only sees it, but it actually identifies it, gives it a unique number, right?
Yes.
You say that? So how long does it retain that number on that image? If it walks out of the image, can it come back and it recognizes that, even if it's been a million things?
Yeah. So, tricky question. There's tuning parameters that can make that better or worse in our system. But essentially, because we have no personally identifiable information and we're only dealing with geometry, once we can no longer see an object, we have no reliable way of saying, now I see that object, I know it's the same one. Because I have nothing that I can match, right, other than geometry. And, if two 5'8", 205-pound guys happen to walk through, I don't know which one's which.
Exactly.
Yeah. As long as I can see the object, the ID sticks. That also includes situations where you can have multiple sensors spread out around an environment, and you bring all those clouds together, you fuse them. This is what I was talking about, multi-sensor fusion. Now I can track across the entire view of the world using 4 or 5 sensors. This is an application we're working on right now with our tracking engine for perimeter security for a government contractor. So they want to put 5 LiDARs out there with PTZ cameras and other radar and other technologies, and do perimeter security at locations that are very remote and unmanned. Like, there's nobody there. There's nobody that's supposed to ever be there. Yeah, absolutely. So there's no degradation in the emitter and the transceiver and receiver of the actual LiDAR. The things that are going to degrade in a spinning, what I would call a traditional spinning LiDAR. The original ones you guys are probably familiar with, they came from a company called SICK. It's kind of like the grandfather of LiDAR sensors. They used a spinning mirror, one laser pointing down at the mirror. Nowadays, you spin the lasers, is how it works. But they're spinning. The only thing that's going to wear out is your motors and your slip rings and your bearings and things like that. I think the MTBF on these systems is somewhere in the 100 to 200,000 hours for the mechanical. Coming into the market now, though, we're in a transformative time for LiDAR. So spinning LiDAR has been the tradition for probably the last 17-ish years. But coming to the market over the last 5 years is this one thing that people call solid state or hybrid solutions. So what these are, the hybrid solutions is the easiest one to explain. Well, I can explain both. But a hybrid solution is essentially a MEMS system. So you use MEMS to steer the mirror, and then you have a traditional LiDAR that's being shot at those moving elements. Those sensors don't have as great of a field of view. In other words, because they're not spinning, they can't see 360 degrees. But in the field of view they do have, they're very, very high resolution, like 80,000 pixels per frame at very little. Matter of fact, that video of the door guard stuff, so that is a solid state sensor, a true solid state sensor. It uses a technology called time of flight, and it is flashing the scene with infrared light, and then essentially like any type of like CCD, it's specially tuned to receive that type of light, and then you get like a pixel image, essentially, right? And you get range and other information about it. It was a really important one we use a lot called intensity. Intensity is just the expression of how much energy came back, right? So more reflective things return more energy, less reflective things return less energy. There's no metric on what intensity of 100 and what intensity of 0 means. Every manufacturer has their own scale. It's just a relative to that particular manufacturer. I can't compare and contrast. So that's a true solid state. And they make solid states that use more traditional lasers instead of the flashing time of flight system. And those are coming on the market. So those systems will be much more reliable, and that's why they're being developed for the automotive market, right? So there'll be shock and vibe and temperature, everything rated that you need to be able to put a sensor on a car, and also size. So that's one of the reasons that graph is so attractive, because the cost is coming down. So here's a really cool thing about LiDAR that I can't say about a lot of things. Cost is coming down. Power resolution capabilities is going up, and size is going down. Show me any other technology you get to choose all three, right? It doesn't exist. So anyways, I hope that was a very long-winded answer to your question, I hope.
Great, thank you.
Yeah, so there's a couple key questions there. So the first question is, what type of range are we getting? So the answer, I can tell you for the solution we're using now. LiDARs as a whole have short-range sensors and long-range sensors. The newest sensors just launched last week from one of our partners is something like 200 to 300 meters it can see. The sensor we're using, like for door guard, much lower cost. It's a good data to about 5, maybe 6 meters. And then the second question, I'm sorry? Yes, or indoors. I mean, the sensor sees 200 to 300 meters. You just wouldn't really need it indoors, right? But yes, and that's what's needed for automotive, right? To get to level 4 or level 5 autonomy, we have to be able to see significantly far ahead. And what's really nice about these sensors is they see significantly far ahead in adverse conditions like darkness, rain. Here's a funny anecdote. I've tested these, so I'm not just telling you it works in all kinds of weather. We had a Navy project, so we tested these in all kinds of weather. I've tested them in fog. Rule of thumb on fog is if you can't see it, the LiDAR can't see it. But if you can see it, the LiDAR can see it. I've tested them in snow, works very well. And I've tested them in 100 inch per hour rain. And if you've never seen 100 inch per hour rain, it's like standing in the bottom of Niagara Falls. It is crazy. And this is the Navy, so this is what they want to do. They say, well, a once in 500 year maximum rainfall at one spot on the earth is 100 inches per hour. We're going to test for that. So it's pretty much a condition nobody will ever see. LiDAR and radar both provide distance information. You can do tracking in radar. It's a pretty well understood subject. But the problem with radar, and it's kind of a traditional problem, is they typically don't work very well if something is not moving, right? LiDAR works very well regardless of what the object you're tracking is doing. So if they come to a complete standstill, because I'm looking at their geometry, I know that they're there. They can't hide from me. The other thing, it was on the slides, but I forgot to verbally mention it, is by its nature, and LiDAR data is very, very difficult to spoof, right? So yes, you could carry a mannequin. That's probably but in general, if you hold video systems, very, very easy to trick. Hold a picture in front of your face of somebody else's face. Problem solved. LiDAR is not susceptible to that type of spoofing. It's very difficult to spoof the geometry of somebody or hide your geometry. So I put in some links here. So I want to kind of reinforce the idea we're not the only ones thinking this way. So there's 4 URLs in here. Some of them are from LiDAR vendors. One's from Triple E. One's from a security magazine. All talking about LiDAR and security. So you can go read that. You can kind of see how the entire industry is starting to coalesce in this direction. Matter of fact, the entire LiDAR industry is starting to coalesce into, well, there's always self-driving cars. Not interesting. But industrial applications, security, people tracking, people counting, things like that. Well, thank you guys. I appreciate the attention.